So far, I've been dealing with a single set and a single operation. This operation had to be associative, have an identity, and have an inverse. We also looked at the special case of it being commutative, which is known as abelian. In this video, I want to look at what would happen if we added a second operation. So we have multiplication and addition. The most basic of the two operational systems is known as a ring. We traditionally call the two operations of a ring addition and multiplication. However, the elements of a ring are not necessarily numbers. So addition does not necessarily refer to our conventional addition of numbers, nor does multiplication necessarily refer to the conventional operation of multiplying numbers. So let's start with actually looking at the definition of a ring. A ring is a set A with operations known as addition and subtraction such that three things are true. The first thing, we need that set A with only the operation of addition to be an abelian group. We need the operation of multiplication to be associative. And we need the distributive property. So for any three elements, A, B, and C in my set A, I need A times B plus C to be equal to A plus AB plus AC, as well as, so this is my left distributive property, I also need the right distributive property, B plus C times A to be equal to BA plus CA. So a couple of key takeaways here. Addition must be commutative, since it does have to be an abelian group. A couple of key takeaways from this definition. Addition must be commutative, since addition must be abelian. Addition and multiplication must be associative, since we have that multiplication is associative, and addition forms a group, which tells me that it's associative. It must have an additive identity and an additive inverse, once again, by the fact that it has to be a group under addition. And my distributive property must hold. A couple of things about notation. The additive identity is typically called the zero element, and it's denoted by a zero. The additive inverse of an element A is denoted by minus A. It's also known as the negative. And finally, we can define subtraction as A minus B is equal to A plus minus B. So we can talk about subtraction under these rings. So let's look at some examples. The easiest examples of rings are just the real numbers. We already know the real numbers form an additive group. We know that multiplication in the real numbers is associative. And we know that the distributive property holds for real numbers. We could also consider the integers z. We've discussed many times how the integers do form an abelian group under addition. We know multiplication of the integers is associative, and we know that the distributive property holds under the integers. Similarly, we could consider the ring of rational numbers or the ring of complex numbers. In a previous video, I talked about this group f of r, and this was the set of all functions. Well, in algebra and pre-calculus, we talk about f plus g of x to be equal to f of x plus g of x. We also define fg of x to be f of x g of x. We could go through and prove all of our properties, but this does give us a ring of real functions with these two operations. So we can also talk about the ring of functions. So far, all of my examples of rings have been infinite rings. They've had infinitely many elements. Well, if we pick any n greater than or equal to 2, then we can talk about Zn. This is a finite ring. We define multiplication by multiplication modulo n and addition by addition modulo n.